Hello, good morning or good afternoon, everyone. My name is Lakshmi Prasad Adusumilli. I'm a senior DevOps lead or cloud lead. I have experience that spans both traditional middleware administration and modern cloud native technologies, making me a versatile technology professional who consistently design cloud scalable infrastructure solutions. Let me begin with a scenario. Imagine a hurricane making a landfall. 911 call volume surge, dispatch systems are under stress, and every second of downtime could cost lives. When we think about emergency response, whether it's dispatching ambulances, coordinating firefighters, or managing disaster relief, downtime is simply not an option. Today, in this talk, I will share how platform engineering, a practice often associated with enterprise IT, can fundamentally transform emergency response systems into cloud native platforms that save lives. In this agenda, first we'll begin with foundations of platform engineering and why they matter for emergency systems. Then dive into self-service infrastructure and developer experience. Third, operational excellence patterns from orchestration to observability. And finally, organization strategies that make these platforms sustainable and adaptable. The challenge. Unlike traditional enterprise applications, emergency systems can't afford even seconds of downtime. They must scale instantly during crisis, integrate with legacy and government systems, and still comply with strict regulations. Think of what happens when a hurricane hits, call volume spike, dispatch systems must respond in milliseconds, and failure could cost lives. Traditional deployment models will, with long cycles and manual process simply can't keep up. We need a new paradigm, the paradigm shift. Before platform engineering, deployment took 2 weeks. Errors were frequent and redundancy was limited. Operation teams are isolated, infrastructure is inconsistent, and geographic redundancy is limited, and specialized knowledge is required. And platform engineering, we achieved three minutes self-service provisioning, golden paths with built-in best practices, and 89% reduction in the config errors, consistent patterns across 200 plus microservices, multi-region deployment by default, and high complexity from application teams. This shift creates multiplier effect. Emergency teams can focus on their mission on saving lives instead of firefighting infrastructure. Coming to Developer Portal is heart of our self-service platform. It acts as a primary interface for emergency response teams, a place where they request infrastructure, deploy services, and monitor their systems. Instead of waiting weeks for manual approvals or writing low level scripts, developers now have a simple gateway that abstracts complexity and provides consistency. Here we discuss about golden path templates, self service catalog, and service scorecards. We'll dive in deep into all these 3 points. Golden path templates. Golden paths are pre-approved templates that developers follow to provision applications and services. They are embedded with security, observability, and compliance best practices by default. Why important for emergency response? During a disaster, developers don't have time to figure out how to configure networking, encryption, and logging. Golden paths ensure all services meet baseline requirements automatically. Let's take an example. A new emergency alert microservice can be deployed in under 3 minutes using a golden path template. It comes pre-wired with centralized logging, TLS security, and monitoring dashboards. No manual work is needed. One of such examples is Backstage, which is Spotify's open source developer portal, often used for Golden Path implementations. Golden Paths might also include Helm chart templates, Terraform modules, or Kubernetes YAML blueprints, and pre-built guardrails. Coming to Service Catalog. The Service Catalog is like a menu where teams can pick the infrastructure and services they need without opening tickets or relying on app ops teams. Self-service provisioning of databases, messages, queues, and caches, object storage, and other cloud-native components. These are all what it offers. Each entry in the catalog comes with built-in processes like HIPAA, NIST, and local regulations. Coming to emergency response scenario, one of the example is suppose an incident occurs that requires scaling up real-time event queue for incoming calls. Instead of days of provisioning, an engineer selects Kafka cluster from the service catalog and has it ready in minutes, pre-configured for resilience. Some of the tools and examples are HashiCorp, Terraform Cloud, Crossplane, or AWS Service Catalog, often powered the backend. Coming to service scorecards. Scorecards provide real-time metrics on health, reliability, and compliance of each service. Think of it as a report card for every microservice. What they measure reliability, uptime, error rates, mean time to recover. They also offer security and compliance. They also measure performance, latency, throughput, and resource utilization. Some of the examples are Prometheus and Grafana for metrics visualization, OpenTelemetry for traces. The conclusion is The developer's portal is not just a dashboard. It's productivity engine, golden paths, where golden paths provide saves faster deployments, service catalog gives instant access to critical infrastructure, and service scorecards deliver real-time visibility. The result is what took 2 weeks now takes 3 minutes. Coming to IAC and GitOps, which are core for this infrastructure. Everything is defined as code and managed through GitOps. We have full version control, drift detection with 100% coverage, and 73% of deviations auto remediated. Immutable infrastructure patterns mean no ad hoc changes. Let's dive deep into the infrastructure as code and GitOps. Infrastructure as in code and GitOps are backbone of reliable cloud-native platforms. They transform how we build, deploy, and manage emergency response systems where consistency and trust are non-negotiable. Let's break down in these practices and why they are critical. What is infrastructure as a code? ISC means we define infrastructure in code not through manual clicks or ad hoc scripts. Everything from Kubernetes cluster load balance to IAM rules is written as declarative configuration files stored in version control. This enables consistency, automation, and version control. Every infrastructure change is tracked in a code without history or differences and rollback ability. Coming to consistency, same configuration is applied across different environments and dev, test, and production. Automation, development, deployments happen via CI/CD pipelines without human error. Some example tools are agnostic IAC tool, provides resources like AWS, Azure, Google Cloud Platform. And also, some other example is Ansible, often used for configuration management and small scale provisioning. A Terraform module, let's take an example. A Terraform module provisions 5 Kubernetes clusters across different regions with identical settings, ensuring compliance and resilience. When a new node pool is added to the handle a disaster load, is done by updating code in Git, not manually. What is GitOps? GitOps extends infrastructure as a code by using GitOps as a single source of truth for both infrastructure and application deployment. Any change to infrastructure or application manifest must be connected to Git. A GitOps controller like Argo CD Flux continuously reconciles live cluster state with declared state in Git. This provides auditability, automatic diff detection, and safer deployments. What is auditability? Every change has an author, commit history, and approval workflow. Coming to automated drift detection, if someone changes a resource directly in the cluster, GitOps reverts it back. And these deployments are also safer, where changes are tested, peer reviewed, and rolled out inconsistently. Some example tools are Argo CD and Flux CD. Coming to key benefits of these emergency response systems are reliability, speed, resilience, and compliance. In short, IAC ensures that our infrastructure is reproducible and predictable, while GitOps ensures that our operations are automated and auditable. Together, they make sure emergency systems stay online, secure, and ready to handle demand spikes when every second truly matters. Coming to multi-cluster orchestration. Imagine a flood knocking out an entire data center. The system must continue running without missing a beat. Resilience is critical. Multi-cluster orchestration ensures that if one region goes down due to a flood, power outage, or cyber attacks, services continue seamlessly. We distribute workloads across 5 regions, maintain active clusters, and prove traffic to the nearest healthy endpoint. Coming to multi-cluster orchestration architecture. We have failover of Kubernetes clusters. We operate multiple Kubernetes clusters per this design ensures that if one cluster goes down due to hardware failure, software bug, or even a recent disaster, another cluster seamlessly takes over. Automated failure mechanisms synchronize stateful workloads across clusters. This means data is not lost and operations can resume within minimum disruption. By regional isolation, we prevent cascading failures. For example, an issue in one region does not spill over and impact others, which is crucial in emergencies. Multiple clusters per region. Within each region, we maintain more than one cluster. This supports active-active configurations where both clusters are live, share load, and improve availability and fault tolerance. During peak load, for example, a sudden 800% spike in emergency calls during a disaster, resources are automatically distributed across clusters. This balances performance and ensures fastest possible response time for first responders. Regional balances, coming to regional balances with redundancy. Each region is front-end by regional load balances, which is distributed incoming traffic among clusters. These load balances themselves are redundant. If one fails, another instantly takes over, ensuring there is no single point of failure. They also support intelligent routing, sending requests to least within the region, emergency services with failover. Each individual emergency service, such as dispatching, geolocation, or medical triage systems, is designed with built-in failover. For example, a primary instance of a dispatch service in cluster A becomes unavailable. The system automatically routes to a secondary instance in cluster B without manual intervention. Coming to global traffic management and failover. This is one of the key component of the architecture. Above the regional level, we use global traffic managers like DNS load or cloud native global load balancing. These systems direct user requests to the nearest healthy region, ensuring edge optimized routing with sub 50 millisecond latency. If an entire region becomes unavailable, for instance, due to natural disaster, global routing automatically fails to another region. To summarize, this architecture combines failover at every level service, cluster, regional, and global with intelligent traffic management. This result is a platform that is resilient, compliant, and ready for the unexpected failures. This architecture ensures that sub 50 millisecond dispatch response times globally. Coming to service mesh integration. A service mesh adds another layers of resilience. It automatically routes traffic to healthy services using circuit breaking to stop cascading failures and enforce mutual TLS security for zero trust security. Even partial failures does not affect system availability, a must for life critical operations. Coming to observability. Of course, you can't operate at this scale without visibility. You can't fix what you can't see. Our observability platform ingests 2.3 million metrics per minute and delivers 99% of alert accuracy through machine learning and anomaly detection. This enables less than 30 seconds. Coming to policy as cloud. Security and governance are non-negotiable. Governance should not slow teams down. By embedding policy as code, security and compliance are enforced automatically. We enforce runtime policies automatically continuously validate against frameworks and secure the supply chain with and provision checks. Example, let us take an example. If a deployment violates runtime security, it is blocked instantly without requiring manual intervention. This approach delivers governance without slowing teams down. Security and compliance are built in default. Coming to platform team organization, is enabled by 12% platform team supporting more than 80 developers. We run the platform like a product, gathering feedback, embedding engineers with application teams, and providing 24 by 7 support. It's about doing things ourselves. It's about enabling others to move fast, safely. Measuring platform success. How do we measure success? Developer experience is improved. 67% faster time to production, 75% fewer stock support tickets. Operational metrics improved, 19% availability, and 78% decrease in mean time to the response or repair. There is 30% reduction in emergency response time, increase in future delivery velocity, and 65% decrease in infra costs. Ultimately, these are not just numbers, they represent faster resources, better outcomes, and saved lives. The key takeaways. To close, service key takeaways are self-service infrastructure unlocks agility, platform abstractions reduce cognitive load, and golden paths enforce best practices. The journey does not start with boiling the ocean. Begin with what golden path, measure rigorously, and expand. When platform engineering meets emergency response, technology directly translates to human impact. That's why this work matters. Thank you.